Friends, you are welcome back to the discussion of the programming language LISP. We were discussing evaluation of S expressions. I'd like to go a little bit more in detail. What is meant by evaluation? We take an example. For example, we have got a problem of farm yield, and in this particular case we know that a particular field, 1 acre gives say 12 tons. So how much yield will be there out of 5 acres? In this particular case we will not go to the field, actual field. Rather we will represent it on the paper, 1 acre ACRE equal to or yields 12 TONS, and so on and so forth. Similarly, when we are talking about say the illness of our dog, maybe having some special name, say devil, so we will not take the dog everywhere unless it is to be taken to the hospital, but we may have a talk with the doctor through symbolic representations, that instead of the animal which has 4 legs etc., which may bark and may even bite, DEVIL may do many of the functions which we want to convey about the animal dog. What I want to convey through this is that the representation and represented entities are two different things. Representations are conveniences. When I write DOG, this word DOG of 3 letters cannot bite. However, it represents something which can bite. So we must differentiate between a representation and what is represented by that representation. The letter, the word DOG is a representation of a biological entity which can even bite. But these are two different things, the word dog and the actual animal dog. Why I have told you that most of the time we work on the representations which are words, expressions, numbers, etc. But those are used to represent something apart from themselves. The word dog does not in general represent the word dog. Rather it represents the animal dog which actually bites, can bite at least. So here a representation represents something else. Whatever something else is there, that is called the value of the representation. And most of the time the purpose is to find out the value, because the whatever is written over there is INCOME. The word income is not of our interest. Rather its value 3,47,000, because we are to compute the income tax. So income word in itself is not of our interest. Rather the value is there, but because the value change from person to person, therefore we are using a word, and for different contexts this word income will have different values as is appropriate for the case under consideration. I hope the difference between the representation and its value must be clear, and therefore whatever is the discussion which we had in the last 5 minutes of the previous lecture, or we are going in the ensuing time, is in this particular context we are using some representations, but the representations are not for their own sake. They are representing something different, and the system must find out that something different which is represented over there. Because in order to find out the income tax, I don't need the word income. I need the amount 3,47,000, which is the entity represented, which is called the value of the word income or the variable income. I hope this clarifies the differentiation. So with this explanation, now we go to finding out the values of various expressions. And I already told you that when in some of the cases we are interested in the word dog itself and not the animal dog, how to represent the word dog. Because if we write DOG, it will be definitely representing an animal. But in case we are interested in the word dog itself, then it is represented generally in the language LISP by a quote preceding it. So quote followed by the word means the word is represented. We have already discussed this thing. So now we will be coming to the discussion of some of the inbuilt functions values. For example, please look at the slide. Now the expression is plus 3, 4, 8, 11, minus 2. Friends, I have already said that LISP language is a prefix notation using language. That is, if you intend to apply an operation on its arguments, then the operation's representation must be the first. So the plus represents the operation and it should come as the very first symbol within the pair of parentheses, and it is applied to its argument. And in the case of LISP, the operation plus may not have just two arguments. It may have a single argument, it may have any finite number of arguments. So in the first line you are having plus followed by 3, 4, 8, 11, minus 2. So what is its implication? What it represents? It represents a single number. How that number is obtained? That is, you add the quantity 3 to 4 and whatever is the result add that to 8, whatever is the result add that to 11, and whatever is the result at that particular stage add that to minus 2. And you can see 3 plus 4 is 7, plus 8 is 15, plus 11 is 26, minus 2 is 24. So, the expression in which the left parenthesis is the first symbol, followed by plus, followed by 3, followed by 4, followed by 8, followed by 11, followed by minus 2, followed by the right parenthesis. Actually it is an expression which represents something. And what is that something? That something is 24. So try to understand the differentiation between representation and what it represents. Similarly, instead of the cross plus, you can write plus also. That is also interpreted by the LISP environment as addition operation whose arguments follow it in the representation. So again plus 3, 4, 8, 11, minus 2 will return the value 24. Next is minus operation, because the minus symbol is the first one, and I have said that within pair of parentheses, if there is an symbol which represents an operation, then it must come first. So here minus is the operation, that is we have to find out the difference of its first argument from second, that is 13 minus 55 is the entity intended to be represented by the expression left parenthesis followed by minus, followed by 13, followed by 55, followed by right parenthesis, which comes out to be minus 42. But in the case of minus, the number of arguments must be equal to exactly 2, and minus symbol, that is a line, short line, may be replaced by the word difference also. So in LISP language, either you write the symbol minus or you write the word difference. Both indicate that the second argument is to be subtracted from the first. That is, in this particular case 53 is to be subtracted from 13, which 55, and the argument in this particular case there is a misrepresentation in the last line, it should be 55, therefore the answer will come out to be minus 42. Then the third inbuilt function is star, multiplication. Star represents multiplication. And because star comes as the first symbol within the pair of parentheses, so it is interpreted as an operation which is to be applied. And again, as in the case of addition, the multiplication also may have any arbitrary finite number of arguments. Here there are 3 arguments, 2 followed by 3 followed by 4, and because the first symbol is star which represents multiplication, therefore the 3 arguments 2, 3 and 4 are to be multiplied. You know, 2 multiplied by 3 gives 6, multiplied by 4 gives 24. But star may be also represented by the word times, TIMES. Next is the slanted line. It represents the division, quotient. That is slash 9, 3 means divide 9 by 3, and whatever is the quotient, you write it over there. So instead of the 9, you can also write the word quotient, Q-U-O-T-I-E-N-T, etc. Friends, again you have got the word ABS, ABS. This is again representing an operation which finds out the absolute value of the number followed it. What is an absolute value? Absolute value of a number is equal to itself if the number is non-negative. And if the number is negative, then the negative sign is removed. Whatever is left is the value returned by the function ABS. So absolute or ABS of minus 5.7 will be equal to 5.7, and ABS of 5.7 will be equal to 5.7. As I just now mentioned, ABS just returns the value after removing the minus sign if it is present, and if there is no minus sign, then the value is as it is given in the argument. EXPT actually represents exponentiation. That is, XPT is followed by two arguments. The first is taken as the base and second is taken as the power. So EXPT 3 followed by 2, the two arguments will be actually interpreted by the LISP environment as 3 raised to power 2, which comes out to be 9. Then the next function is SQRT. SQRT actually represents the operation of taking square root. And square root of 4.0 we know is 2.0, positive square root. There, because any number may have two square roots. One is positive and the other is negative. However, SQRT represents the positive square root of the number which is given as its argument. So square root of 4.0 is plus 2.0. Max. Again, max, like addition and multiplication, may have any finite number of arguments, and what it does, it finds out the maximum among the given arguments and returns that is its value. So max 8 followed by 11 followed by 9 followed by 7, it finds out the maximum of the numbers which are given as its argument 8, 11, 9 and 7, and as we know 11 is the maximum of these four numbers. Therefore 11 is returned as a value of the expression in which there is pair of parentheses and within which the first word is max, first symbol is max, followed by a list of numbers. Similarly, min returns the minimum. And you can see the minimum of the four numbers 8, 11, 9, 7 is 7, therefore 7 is returned. Now there is another operation which is represented by the word truncate, means that it gives the integral part of the number written after it. So if we are given 14 divided by 4, so it will be returning 3 because 14 divided by 4 will be 3 point something, and that something will be removed and you will be getting the number 3. Rem 14.4 gives that whatever is the remainder after division by the second argument of the first. So Rem 14.4 actually means that when we divide 14 by 4, we have 3 as quotient and 2 as remainder. Therefore the remainder 2 is returned in this particular case. Similarly, friends, we have got other function rounding. We know very well that rounding means that whatever is the nearest integer that should be returned. So if a number 14.3 is given, the nearest integer to this is 14 and not 15, therefore 14 is returned. However, if we have the argument 14.6, now we know 14.6 is closer to 15 as compared to 14, therefore the value 15 is returned, not 14 is returned. However, in the case of truncation, it must return 14. In the case of truncation, the decimal part is cut off, it is removed. In the case of round, it is a bit different in the sense that it attempts to find out the nearest integer, because 14.7 is 6 is given as an argument, and then we find out how far it is from the nearest two integers, one is 14 and one is 15, between which 14.6 lies, and we know that distance of 14.6 from 14 is 0.6 and the distance of 14.6 from 15 is 0.4, which is less, therefore the value returned is 15. Float 14. Sometimes we want to represent an integer as a floating number because the representation may require more bits and bytes and for the purpose of arithmetic operations. So we may convert an integer into a floating point number in order to get larger bits, and that can be done by writing float. Float 14 will represent it as a 14.0, that is, an integer becomes a real number in the internal memory. Now friends, we have discussed a number of inbuilt functions in the programming language LISP. However, while solving problems, inbuilt functions may not serve our purpose and generally don't serve our purpose. That is, a programming language must make provision for the functions to be defined by the user. There must be some mechanism by which the user can define new functions suitable to the solution of the problem under consideration. There must be a syntax for doing that. So next we discuss how functions are defined in the language LISP. Please look at the slide. The slide says that whenever we have to define a function in the language LISP, the structure of that will be something like this, that first of all a left parenthesis should come, and at the end a right parenthesis must come, and in between there will be a number of expressions. The first expression must be a symbol which represents the name of the function to be defined. For example, if you want to find out the sum of the squares of two given integers, we may give the name SUMSQ. So whenever we have to define a function, first of all we have to find out the name of the function and then its parameters. Friends, we will discuss the defining mechanism later on. At present we assume that some of the functions are defined by the user. Then how we find out the values of those where the functions have been already defined, because the defining process is a bit more difficult than evaluation of a function. Therefore, first of all we will discuss how a function which is already defined either by the user or by the system, how it is evaluated. We have already discussed the evaluation of some of the inbuilt functions. Now we will discuss the evaluation of the sum of the function which may not be defined by the system but might have been defined earlier by the user. So how it is evaluated is the major issue under consideration. For this purpose, let us take some examples. As we have already done, that if star 411 is given to us, we discussed earlier inbuilt functions, but we didn't go into the details how various steps by the system are taken in order to evaluate the expression star 411. Friends, what is done is something like this, that whatever is the first symbol, in this particular case star, it is seen what it represents, and it is a standard symbol. It represents the operation of multiplication. The multipliers within the computer system are activated. Then the next symbol, which here in this particular case is 4, and we know a number is represented, a number is evaluated to itself, so 4 evaluates to 11. 4 evaluates to 4, and 11 evaluates to 11. Therefore, these two values are now given as arguments to the multiplication system, and ultimately 44 is returned. In this particular case, it may appear that I have said something special. However, if some of the symbols are given instead of numbers, then you will understand the explanation has some relevance. So let us take an expression plus followed by star x3 followed by minus y1. Now in this particular case, x and y are symbols which are not numbers. And here the evaluation of the arguments of the operations which are inbuilt in this particular case will become more clear. Suppose that x has already been bound to 2 and y has been bound to 5. Then what the inbuilt system will do? That first of all, in order to apply star to x3, it will find out the value of x, which is 2, and the value of 3 is 3. Therefore, now the multiplication operation is applied to two numbers which happen to be 2 and 3, the result of which will come out to be 6. Similarly, if y is associated with number 5 through some other way or construct, then when the expression minus followed by y followed by 1 is evaluated, first of all the value of y is found, which is 5, and therefore the difference operation is applied to two numbers 5 and 1, and in this particular case the value returned is 4. So the two parts or two arguments which themselves are list of the operation plus have been evaluated. The first argument evaluates to 6 and the second argument evaluates to 4. And then these two arguments are supplied to the operation of plus, which will be returning 24 or something like that. So this explains how an expression, particularly an arithmetic expression, is evaluated by the LISP environment. I hope it clarifies the evaluation of the function by the inbuilt mechanisms in LISP. We take another function which is not inbuilt but rather is defined by the user. Let us call it sum sq. What is the rule? We will assume that the definition has already been given by some construct which we will discuss later on. And what sum sq does, it takes two arguments, finds out the squares of its arguments, and then adds the squares which have been found out. This gives and returns the value. This is the role of the function sum sq. For example, we have the last but one line, sum sq star x3 minus y1. Now the two arguments, as I have mentioned earlier also, whenever a list is there, it is treated as a single element of a larger list. So star x3 will be treated as one element, minus y1 along with the pair of parentheses bounding it also is treated as one, and therefore these two represent two arguments to the function sum sq. So in order to apply the function sum sq, first of all we must evaluate its two arguments. One of the arguments is star x3 bounded by a pair of parentheses. How to evaluate it? We know that whenever a symbol star is there, it is treated as an operation, and in this particular case the operation of multiplication. Then the next symbol or number is evaluated. In this particular, it is a symbol x. So x is evaluated and we say that x has been assigned earlier a value of 2. So x will be evaluated to 2 and 3 will switch self. Therefore star is multiplied, that is the multiplication operation is applied to 2 and 3, which returns 6. So whole of the expression star x3 bounded by pair of parentheses is replaced by 6. Similarly minus y1, where y is bound to 5, is replaced by 4. Now sum sq is applied to two its arguments. One is 6 and the other is 4. So what it will return? It will return the square of 6 and the square of 4 added together, and we know the sum of square of 6 is 36 and square of 4 is 16, which adds to 52. Therefore the whole expression sum sq and then star x3 bounded by a pair of parentheses followed by minus y1 bounded by a pair of parentheses returns 52. Friends, in addition to user-defined functions, there are some special forms which serve a special purpose in language LISP. Just now we said that x is associated with value 2. Y is associated with value 5. We assumed it without knowing the mechanism of associating these values. So these special forms do this type of jobs which we will discuss now. One of the jobs which is very important is associating values with the variables used in the program. And as I said, the values may be depending upon the context. When it is the income of Ram, it may be the word income or the variable income may be associated with 3,47,000. But when the income is in context of Abdul, the value of income may be 5,87,000 or something like that. So friends, what I mean to say that special forms are useful in doing some special roles, and we discuss some of these special functions. The first of all is the set queue operation, quote operation. As I mentioned earlier also, sometimes we are interested in the word dog, not the animal dog. However, how DOG represents the animal. So how to represent the word dog? So every language provides a mechanism by which the word dog and not the animal dog is also represented. And in LISP, we use a quote. Instead of using the quote symbol, we may write the word quote also, Q-U-O-T-E. So what is the evaluation of quote is that you remove the quote and whatever is left out, you just give that its value. So whenever you have a pair of parentheses and in which the special word Q-U-O-T-E occurs and then some expression occurs following it, then the value of that will be the expression after removing quote. So quote and a list *37 bounded by pair of parentheses, the value of that comes out to be *37. Similarly, quote can be used in a number of ways. The most important special word is set queue. What is the role of set queue? That it assigns values to various symbols or variables which are used in a particular program. As I said, that x may be bound to 2, y may be bound to 5, and then we found out the value of some SQ, etc., etc. Now, how we bind the value 2 to the variable x, how we bind the value 5 to the variable y, this is what we discuss now is done in LISP. Please look at the slide. The slide says set q x27. What it does? First of all, it finds the value of the second argument, which is a number 27. The value of 27 is 27. Therefore, 27 is associated with the variable x. This set q, the word q is actually quote, and quote is applied to the next argument, which is x in this particular case, and quote x evaluates to x. So we in brief write set q, which is nothing else quote of the next, which is, and on evaluation the quote is removed. So here in this particular case, set q x actually means set followed by quote followed by x. But we know quote x should evaluate to x. Therefore set q x27, what it does, it associates the value 27 to the variable or the symbol x. Similarly, set q x followed by a list *35 bounded by pair of parentheses. So in this particular case, the symbol x will be bound by the value of its argument, which is the list *35 bounded by pair of parentheses. But we know *35 bounded by pair of parentheses when evaluated gives 15. Therefore set q x, that is the x will be associated with the value 15. However, we must be very careful. If we have set q x quote and then the list, then in that case x is not associated with 15, rather it is associated with the list. star 3 5 bounded by pair of parentheses. Friends, I again warn, I again caution you that the number 15 and star 3 5 bounded by pair of parentheses are two different things. 15 is a number which is represented by star 3 5 bounded by pair of parentheses if it is evaluated, But otherwise, you know, star 3 5 bounded by pair of parentheses has 5 different symbols in it, and these are not directly equal to 15. These are equal to 15 if and only if a system evaluates it. That is, a system applies multiplication to its two arguments, namely 3 and 5. So only on evaluation, star 3 5 bounded by pair of parentheses becomes 15. Otherwise it is not. Friends, we discuss something else further. That set Q need not be applied to associate values to just one argument. It may be used to associate a number of values to a number of variables or symbols. So a single set Q may associate values with 3 or more or 5 variables. In this particular case, set Q X, quote 1, 2, Y 7, Z 11, what it happens that X is associated with the list 1, 2 because quote 1, 2 evaluates to the list 1, 2. 7 evaluates to itself, therefore this set Q associates the value 7 with the variable Y, and similarly the value 11 is associated with the variable Z. I hope it is clear that a single set Q can be used for associating more than one values to the symbols or the variables mentioned in set Q. Again, we must be very clear that list 1, 2 and the number 1, 2 are two different things. List 1, 2 has only one element, whereas 1, 2 is just a number, it does not have any element. Now, again, I explain that whenever set Q X7 something like that is given, the system evaluates and returns the value. What is meant by return? Return means that can be further used in another arithmetic expression or for evaluation of some other arithmetic operation. For example, plus set Q X7, set Q Y3, it does two things. One of the things it does is that first of all, X is associated with the value 7, Y is associated with the value 3, and not only that, set Q X7 not only associates the value 7 to X, but it returns it. What is meant by return? That whole of the expression set X7 bounded by a pair of parentheses may be replaced by the number which has been associated with the variable X, that is 7 is returned as a value also in addition to being associated with the variable X. Similarly, when the value 3 is associated with Y, not only that, but the value 3 replaces set Q Y3 also. That is, after this set Q operations, you will be getting plus followed by 7 followed by 3, which comes out to be 21. Plus, because plus is there, not 21, rather 10. So we should be clear that set operation not only associates values with the mentioned variables, but rather it returns the values also, which can be used in other arithmetic operations, etc. Friends, we have mentioned earlier that LISP is not designed for numerical operations. Mainly it has been designed for list operations or character operations or string operations. The main thing. So, whatever operations we have discussed so far, plus, minus, multiplication, division, etc. Well, of course, these examples have been used in order to make you familiar with the language LISP, but these are mainly not used while writing programs in the language LISP. The operations which are generally used in the language LISP while writing the solution of a particular problem in language LISP are the list operations. We discuss some of the major list operations which are available to us as inbuilt. The others may be defined by the user using these inbuilt list operations. Please look at the slide. One of the operations, please look at the slide. One of the very important operation is car. Car means that you are given a list of elements. You want the first element of the list. For example, if you have got, say, a list of people who have to be given their salary, so the first element may be taken and he or she may be given the salary. Then you want the next element, next name, the third name, fourth name. So what you can do? You can write all these names in the form of list, and the car operation returns the first element of the list, and with this element you can do whatever operations you want to do. Then whatever is the remaining list, you can take the car of the next and so on and so forth. So friends, car is a list operation. That is, it can be applied only to list. If you try to find out car of a number, it will give an error. If you try to find out the car of a symbol, it will give you an error until the symbol is associated with the list. So car must have its argument a quoted list. Why quoted? Because the arguments are evaluated, and in the process of evaluation the quote is removed. For example, quote DBC list. Then if you evaluate quote DBC, the value returned is DBC list. Car means that whatever is the list is obtained after evaluation, that is after removal of the quote, you take out the first element of that. So first element in the case of example 1 is D. Therefore car quoted list DBC gives the first element D as its value after application of the operation of car. So that is D is the value which is written. Next we take another little bit complicated example. Car of a list in which the first element is not a ordinary element but itself a list, and the list contains two elements. And I have told you, whenever we consider list and some element is a list itself, then the whole of the list is treated as a single element. So in this particular case, the list DB and not the element D is returned. So car quote list in which the first element is the list DB. Then in that case the value of the which is obtained after application of the operation car is the list DB. Please note this point. Similarly, if a car is applied to a list and the result returned is a list itself, then you can apply another car, because a car can be applied only to a list. So in this, the third example, we are saying apply car to a list in which the first operation is car, that is, you will find out the car of the list given as an argument of the second car, and whatever is the value returned, in this particular case the list DB, then you again further you have to apply car to that returned list which is the first argument of the second car. So in this particular case, when DB is returned, a car is applied to it and D value is returned. Okay. Similarly, car of a list, the first element, LISP is an AI language. This list has 5 elements. First element is LISP, the second is, third is an, fourth is AI, and fifth is language. And the car of this list returns the first element which is a LISP, which is the word or symbol LISP. Now again, as I mentioned earlier also, that set QX something not only associates the value of its argument with the symbol, but it returns the value. For example, set q x quoted list ABC, then the quoted list ABC is evaluated, which comes out to be the list ABC, and this is associated as a value of the symbol x. Not only that, the list ABC which is obtained by evaluating quote ABC is also returned. That is, return means that can be used instead of whole expression set q x quoted ABC. So the value returned is ABC, and because it is a list, therefore we can apply car to this, and you know car of the list ABC is nothing else but A. Second major operation is CUDR, which is written as CDR. What is the role of CUDR? That you might have processed the first element, but you want to maintain the remaining part also for further processing in future. How to obtain the remaining list? The remaining list, which is obtained by dropping the first element, is obtained through CUDR. CDR is read as CUDR. So CUDR, please look at the slide. CUDR of the list DBC. First of all, I must make it very clear, like the operation car, the CUDR also takes only a list. If a list, quoted list is not supplied as its argument, then there will be error. So CUDR, quoted list DBC, and what it does, it drops the first element. Whatever is left in the list is written at the value of the CUDR of the list. So in this particular case, CUDR quote DBC will return the list BC. CUDR of DBC, please note it. Now the list in the second case has only two elements. One element is the list DB and the second element is the element C. But the first element is to be dropped in the CUDR operation. Therefore we will be left, if you cross out DB list, we will be left with the list C. So friends, these are two very important operations in the language LISP, namely the car operation and the CUDR operations. These play a very important role in writing programs for the language LISP. We will discuss a number of other list operations in the next remaining lecture at 1 o'clock. Till we say goodbye. Thank you.